I thank you for honoring me to be your presenter today. My intention today, I'm going to handle alternating current. Um, yes, okay. We are going to handle alternating current circuits, normally called AC circuits. Alternating current is number 7 of our structural paper. You know, section C has 3 numbers, 5, 6, and 7. 5 and 6 are handling magnetism and electromagnetism. Then number 7 is the one that handles alternating current circuits. Now, what is a circuit? A circuit is a circuit is a continuous pathway between the terminals of a cell through which an electric current flows. And then we have many types of circuits. But the ordinary circuits that we have a DC circuit in which the source is represented by an arrow of this kind. Positive terminal, and that is a negative terminal. And we have another type of circuit called alternating current circuit. For it is represented by this, whereby the current reverses many times per second from one terminal to another of a given voltage V, and F is the frequency upon which it moves. Now, when a coil is rotated in a magnetic field, the flux linking it changes and an EMF is induced. And this induced EMF varies sinusoidally with time, and this leads to an alternating current. Now, look at the circuit here. We have a coil that is placed in a magnetic field, the flux density B, and the coil is rotating at angular velocity W. Now, the angle the field makes with the normal is theta, and therefore the component of the magnetic flux density normal to the conductor or to the coil is going to be B cos theta because it is adjacent to the coil. And therefore, from Faraday's law, induced EMF E is equal to minus L is equal to minus N divided by dt, where N is the number of turns, phi is the magnetic flux, T is time, negative is scattering for Lenz's law. And now, but phi is given by Bn, where B is the magnetic flux density and N is the area of the coil. Therefore, when we substitute in the expression for induced EMF E is going to be equal to minus N. We can try to pull out B in phi, and then NB N. It's going to be equal to minus M NN divided by, that is dB by dB by dt. where that one is going to be, we can even remove the b, and then we remain with b cos b by dt cos theta, where theta is equal to wt, which is the angular velocity. So in this case, we're going to be having E is equal to minus NLB d by dt wt or cos wt. So we differentiate with respect to wt. Now we first differentiate the angle. When you differentiate cos of wt, we'll be getting minus NLB w, and then we differentiate the ratio, which is now going to be minus sine wt. So this negative cancels with that, and we remain with w and lb sine wt. And then this one turns out to be equal to the peak value, which is E naught sine wt, where E naught is equal to w now. So this expression is the expression for the instantaneous value of the EMF that is induced. Now you note from our introduction we say when a coil is rotated in a magnetic field, the flux linking it changes and an EMF is induced, which varies sinusoidally with time, and this leads to an alternating current. So the current arising out of this is what we are going to call the alternating current, given by I equal to I naught sine wt. Now, we continue with terms that we are going to employ in our study of this topic of alternating current. We are saying alternating current, by definition, is one in which the drift velocity of electron reverses many times per second, meaning that this type of current does not flow in one direction, keeps on changing direction at the frequency of the alternating current, as we'll be seeing in the details. The second term, which we're going to handle, is called sinusoidal alternating current. Sinusoidal alternating current is the periodic current whose time dependence is given by the sine function. Sinusoidal alternating current is the periodic current whose time dependence is given by the sine function. The graph you are seeing there is a graph showing how the EMF varies with time as the coil is getting rotated in the magnetic field in that direction of the clockwise direction. So, you are going to see we are putting time boundaries. When you look at this graph, let me illustrate slightly. This is the EMF. This is the graph. This is 0. This is the variation of the EMF. And then that is the peak value of alternating current. That is from that point to that point. And then we are aware that the angular velocity W is equal to 2πf, but frequency is inversely proportional to the time period. So that one turns out to be W equal to 2π over T, since F is equal to 1 over the period. So that one will imply the time t is always going to be equal to 2 pi over W. And time t is the time taken for one complete cycle of a wave. Now that means for a full complete cycle of a wave, the time taken is going to be 2 pi over W. Therefore, half a cycle is going to be equal to pi over W. 3/4 of a cycle, this is going to be 3 pi over W. And so on as the wave continues. That is going to be 4 pi over W. And this is the time axis in seconds. So, the alternating current varies as the sine curve with the voltage. Now we go to the next term, and that is a cycle. A cycle is one complete alternation of the current. The fourth term is frequency. Now, the time frequency is usually defined depending on the aspect of constant. When we find frequency in terms of alternating current, we say is the number of cycles which the current undergoes in 1 second. But when we are defining frequency of a wave, we say frequency is the number of cycles the wave undergoes in 1 second. The fact that we are dealing with current here is the number of cycles the alternating current undergoes in 1 second. The SI unit is hertz. Then the fourth term, which we are going to be handling, is period T. Period is the time taken to complete 1 cycle. And 1 over T, frequency is equal to 1 over T. And therefore T is equal to 1 over F. Then 5, peak value of alternating current. The peak value of alternating current or voltage, peak value of alternating voltage, which are represented by E naught, is also called the amplitude of the alternating current. When you look at the graph, you could realize that the maximum value of the current is what we call the peak value or the amplitude of the alternating current. Is defined as the maximum value of the alternating current. Similarly, of the alternating voltage. Similarly, peak value of alternating current is the maximum value of the alternating current. Number the seventh term is what we call the instantaneous value of EMF, denoted by E. This is the value of EMF at a particular time in a cycle, meaning that at any point as the coil rotates in a magnetic field, at any point there is an induced EMF at a particular time t, and that particular EMF is what we call the instantaneous value of current, given by E equal to E naught sine WT, where E naught is the peak value or maximum value of alternating current. The terms here, W is the angular velocity, whose SI unit is rads per second. The E naught is peak value of alternating current, SI unit is volts, time is in seconds. Number 8, and our last term is called root mean square value of the alternating current, which was symbolized by IRMS. This is the value of steady current. By steady current, we mean direct current that dissipates heat in a given resistor at the same rate as the alternating current. Now, that definition, there are key words to be particular about. When the article there is missing on alternating current, the definition does not count. Why? We are saying root mean square value of alternating current is the value of steady current, which dissipates heat in a given resistor at the same rate as the alternating current. When we say at the same rate, we mean at the same power. When we are making the word there, because the nature of the alternating current that will dissipate the same heat in a given resistor at the same rate as the nature of alternating current has to be particular, as you are going to see in the next illustration. Now you're noting, if we suppose to, we are saying, what is that definition? And why are we particular on the article there? We are saying that suppose two resistors of the same resistance are carrying alternating current, and the other is carrying a direct current as shown below. You look at the diagram. Now, you are going to note that if both distance dissipate the same power in form of heat, then the value of alternating current at that moment is said to be equal to the value of the direct current. And that value is what we call the RMS value of the alternating current or voltage. Now, for our circuit, look at these circuits. The first one is alternating current circuit across the resistor R. This is the voltage supply, and then this is the current. I'll call it I direct current. And then the second circuit is also across the same resistor. And then this is varying in a sinusoidal way. This is the AC source. So the current moves in this direction and at one time, and another time is moving in the reverse direction. So that's why you're seeing the arrows are showing the reverse movement, meaning that it changes direction several times per second. Now, power dissipated for DC is going to be called IDC squared R, and then power dissipated for SC. Usually, we use average power because the directional current is keeping on reversing many times per second, so you cannot get a certain power for one direction. So we get the average current for either direction of current. And you symbolize it by a letter P in those brackets. And that's going to be called I squared R, where I is the alternating current. Now, if P prime, which is for direct current, is equal to the average power P, then that one will imply that IDC squared R is equal to I squared R. And that one will imply, therefore, that I squared DC is equal to I squared average current. And finally, it will imply, therefore, that I which is for direct current, is going to be equal to I squared, good, and then we apply a root. Now you are going to see that this value of direct current is what we call the root mean square. That is IRMS. So direct current becomes equal to IRMS value of current. But the IRMS value of current that's equal to direct current should only be true. This is only true when the power dissipated is equal to the average power. Therefore, when you define alternating IRMS value of current as an alternating current, all those definitions will not count, because the nature of current we are dealing with should be specific to a value that dissipates the same power. And therefore, when you miss the article there, you'll be missing out. So that value of direct current that will dissipate the same power as the alternating current is what we call the IRMS value current, and the root mean square value of the alternating current. Now, you're noting that the RMS value of current is related with the peak value of current by the formula I RMS equal to I naught root 2. Now we need to know how derivation, where are we getting that formula, and how can we show that RMS value of current is given by that value. Now you're noting that since in the alternating current, I is given by I naught sine WT. And therefore, instantaneous power dissipated in the resistor, power dissipated, I will call it power instantaneous, meaning that power at a particular time t is usually given by I squared R, which is the same as I naught squared sine squared WT R. That is the instantaneous power of alternating current. The average power, which is denoted by average of that kind, is now going to be equal to I naught squared R, then the average is that one, but the average sine squared WT from trigonometry is equal to a half. And therefore, average becomes equal to I squared R times a half. And that is the expression for the average power. But we had noted earlier, for root mean square value, the average power should be equal to the alternating current power for direct current. Therefore, power for direct current is equal to IRMS squared R from the definition of root mean square value of current. And these two, the average for power for direct current is equal to power for the average, and therefore that one is going to be equal to, will imply ms squared r is equal to I naught squared r times a half. The r's can go, and then we end up getting IRMS equal to the square root of I naught squared over 2. And finally, the expression turns out to be I naught squared I naught over root 2. So the relationship between root mean square value of current and the peak value of current turns out to be equal to IRMS equal to I naught over root 2, which if you compute, it will be giving you 0.7 amperes. So that is how we can derive an expression for the root mean square value of alternating current in terms of. How about root mean square value of alternating voltage? The definition is going to be the same. We are only substituting where there is current, and then we put there voltage. By the fact that voltage does not dissipate heat in a resistor, we are going to substitute the word heat by electrical energy. And we simply define root mean square value of alternating voltage as the value of steady voltage which dissipates heat, which dissipates electrical energy in a given resistor at the same rate as the alternating voltage. We are still emphasizing the word article there, the alternating voltage. And be keen to this one. Whenever we say define root mean square value of alternating current, we define in terms of alternating current. When you say root mean square value of alternating voltage, we define in terms of alternating voltage. Some learners have a tendency of answering the reverse way. You are told to define root mean square value of alternating voltage, you simply say is the steady value of alternating current. And yet the question is emphasizing alternating voltage. The derivation is almost similar. The only difference in this case is that we are going to be eliminating the current aspect. And then we say that generally what is known is that power is equal to IV. For alternating current and voltage, I is equal to I naught sine WT. And alternating voltage is going to be I V naught sine WT. So it is IV, which is the same as I naught V naught sine squared WT, because it is common. And therefore, we can substitute, we can eliminate current from Ohm's law. It's going to be V naught over R sine squared WT, so which turns out to be equal to V naught squared R sine squared WT. That will be the expression for the power at any particular time t. We call it instantaneous power. Now, that instantaneous power, average power, is now going to be equal to V naught squared over R. Then the expression here is going to be average but average power, the whole of this one, is equal to a half. So we substitute here. So this is going to be equal to a half V naught squared over R. That is going to be the expression for the average power. But as we said in the previous derivation, that the power for direct current is equal to the average power, and therefore for direct current, the, the average power is now going to be equal to I squared power for direct current is going to be equal to IV RMS. So when we substitute for current, so it's going to be V RMS squared R V squared over R, and that power is equal to the average power. So it is now going to be equal to a half V naught squared over R. So a half would go, and then we end up having implying VRMS is equal to the root of V naught squared by 2. So finally the expression turns out to be equal to V naught over root 2. So that will be the expression for the root mean square value of the alternating voltage. Now, we are going to note in AC appliances and voltages, it is the RMS value that is quoted. All the appliances you see, when you see a kettle indicated 240 volts, that value is an RMS value of the current or voltage. So in our calculation, all the values that will be quoted will be regarded as RMS values, not peak values of current, as you are going to see in the examples below. The first example, a vacuum cleaner has a rating of 11 amperes and is connected to 120 volt supply. So we have to determine the peak value of alternating current and also peak value of the alternating voltage. Now, look at the interpretation. We are saying the values that are quoted on our vacuum cleaner is RMS value of current and RMS value of voltage. And therefore, we are indicating it as 11 amperes and 120 volts. Now, from our formula, IRMS equal I naught over root 2. So we are only substituting. Make peak value of I naught the subject of the formula. It is now going to be the peak value is going to be called IRMS, which is 11 root 2, and gives the answer to be 15.56 amperes. And root mean value of alternating voltage, we use the same formula. The voltage was given as 120, so we substitute in the expression, and then we finally get the answer to be 169.7 volts. Question 2. We have an electric kettle, draws 1.5 kilowatts from a 200 volts main supply. Now we have to find the amplitude of current drawn by the kettle. Now the value of power that is given is also an RMS value of power. So P RMS is given as 1.5 kilowatts. Kilo means 1,000 watts. And then the voltage supply, the voltage also is VRMS, which is given as 250 volts. So our interest is get to the RMS value of current from which we'll get the amplitude of the EMF of the current. So from here now we are saying PRMS is equal to IRMS VRMS. So implying that IRMS is now going to be P, is going to be P over VRMS. So which is now going to be equal to 1.5 times 10 to the 3 divided by 250. This is PRMS. Divided by 250. And therefore, the value for IRMS is now going to be for 6 amperes. Now, after getting IRMS, you know the relationship between IRMS and the peak value of the current, I naught over root 2. So we substitute in the values, and therefore we obtain our IRMS to be equal to 6 root 2. And we don't give the answer in roots. We give complete answer, the 8.4, 8.5. Okay. So that's going to be the peak value of the alternating current, or the amplitude of the alternating current. Number 3, we are given instantaneous value of sinusoidal alternating voltage as V naught, V equal to 399 sine 120 pi t, and V is given by V naught sine WT. Now by comparison, V equal to 399 sine 120 pi t. We compared it with the expression for the instantaneous value of alternating voltage, which is V equal to V naught sine WT. Now you can call comparison, you could realize that V naught is compared to 399 and WT is compared to 105 pi t. So that one implies that V naught becomes equal to 399 volts and W becomes equal to 125. So now from this expression we can get frequency. W is equal to 2 pi f, and it is equal to 120 pi. Now you could realize f is equal to 120 over 2, which is 60 hertz. So that is the frequency of the alternating current, which you can obtain that way. Then start from now, how about the root mean square value of the alternating voltage? Now from that one you have already got 399 as your peak value. From the expression for V, RMS is equal to V naught over root 2. You can now get the RMS value as 399 over root 2. So this was Roman 2. This was Roman 1. So you could easily get the answer in this. Question 4. Define amplitude of alternating current. That one, we say the amplitude of alternating current is the same as the peak value of the alternating current, which is the maximum value of the alternating current. Then sinusoidal alternating voltage is given as 170 sine pi t volts. Is supplied across a resistor of resistance. That one. So now our interest is to obtain the RMS value of current which flows, the current, the frequency of the alternating current through the resistor, and then the average power. We are also making a comparison. V equal to V naught. V was given as 170 pi t. This was supposed to be sine 120 pi t. We'll make adjustments in that formula. And therefore, if we make a comparison with V, V naught sine Wt, we end up realizing V naught is equal to 170 volts, and then W equal to 125. So implying that the frequency W equal to pi f, 120 pi, the frequency turns out to 60 hertz. So if our interest is to get the value of the current, we are going to first of all use the expression to get the peak value of alternating current. So we can now say V from Ohm's law, V naught is equal to I naught R. So it will imply that I naught is now going to be V naught over R. And then the V naught is given as 170. If we divide it by the resistance, which was given as 100 volts, so we end up getting peak value of current to 1.7 amperes. But the question is interested also in getting the frequency, so meaning that the frequency I've already got it as 160, then the peak value of current we have got it as 1.7 ampere. Now we can also get the RMS value of current. RMS is equal to I naught over root 2. It gives 1.7 over root 2. And then we can also obtain the answer to be 1.2 amperes. That is the RMS value of the alternating current. Then average power. There are very many ways of obtaining average power since we have all the values. We can either use average power as equal to RMS square R, or we can also say average power as I naught square over 2,000. Or we can use average power as RMS as V square over R. naught squared over r. Any of the values used will give you the same answer. So you can say RMS value goes up as 1.202 times the resistance R. So you can get the power to be equal to 144.48 watts. Even if you substitute in the other previous expression, because earlier on we had got the expression for power in our derivation previously as v squared over 2r. So if we substitute here, v naught squared is 170. 2r is now going to be 200. So the answer is now going to be the same answer as 144. So we are about to conclude. We are concluding our lesson by an activity. In that activity, you are the one going to work it out. The first one is as you see on the screen. You are given the value of the alternating current, and then you are given the resistance of the kettle. So you have to determine the mean power rating of the kettle. You have provided the answer, and for part, the answers for you have to work out to verify those answers for either part 1 or part 2, and also for transforming for that part. So any communication or anything that you want for clarification, I'll be getting the feedback on the platform, and we'll be continuing in the next session. We'll be continuing with how to determine alternating current. And those instruments that are used to measure alternating current, we usually call them square law instruments. Why? It is because alternating current varies many times per second. So ordinary instruments like ammeter or voltmeter cannot measure alternating current because their current keeps on keeps on changing. And those instruments use torque in a rectangular coil. So that means it will add the coil clockwise and anti-clockwise at the frequency of the alternating current, so the point will end up deflecting along the same position. So you can read ahead by reading about measurement of alternating current using a hot wire meter, measurement of alternating current using an iron meter. You can use a repulsion type and an attraction type. You can also use a thermocouple meter. You can also use a rectifier meter. So when you go through, by the time we handle the next lesson, we would have found it very easy. How I wish you good time. Nice holiday.